So today's speaker is Barbara Emery, and she received her doctorate in meteorology from MIT with a thesis about neutral winds and temperatures in the thermosphere deduced from the Millstone Hill Incoherent Scatter Radar. Following that, she did a postdoc in France, where she again worked with ISR data and helped take monthly World Day data from various sites. And after that, she came to Boulder to work at NCAR, where she studied auroral processes using data and models with Ray Roble and Art Richmond at HAO. And for a long time, she's been a core member of the CDAR database and organized many of the CDAR workshops during her time. And after she retired in 2015, she started, as she says, a second career as a water aerobics instructor for the city of Boulder and YMCA. And recently, she has been doing some work on solar physics, working on studying magnetic fields on the sun using the recently digitized Mcintosh archives of Carrington maps, which is what she will talk about today. Go ahead, Barbara.
Okay, thank you, Nick. And welcome to oscillations in the magnetic inversion lines on the sun. And it's over 5 solar cycles. We have 55 years worth. Let me see if I can not advance this. So my co-authors are Sarah Gibson is one of the leads. Dave Webb at Boston College is our main lead. Ian and Bob work with me here at HAO, and then Tom is working with Dave at BC. So what we're looking at is where the magnetic fields lie on the sun. And as we know, there's an 11-year, actually a 22-year magnetic cycle on the sun. And we actually do see a 22-year periodicity in some of the things that I'll be showing later on. The plot to the right shows the latitude location of I gotta back up all the time. So this is the latitude location, 40 degrees on the sun, plus and minus, because we flopped over the southern onto the northern side. This is 60 degrees. So in between 40 and 60 degrees, the polarity inversion line, or the filaments, are line most of the time until at solar minimum, which are these dashed lines. Then they start their rush to the pole, this RTTP. And so the red is the southern hemisphere, and it actually ends later than the northern hemisphere. These are Carrington rotations on the bottom. But they rush up to 80 degrees, and then they disappear, and you change polarity. Meanwhile, the secondary neutral lines, or polarity inversion lines, are coming up about 15 degrees lower in latitude, and they come to their own peak at the end of the rush to the pole. And then what we see is this oscillation down toward the next solar minimum. And we see approximately a 20 Carrington rotation oscillation. And that's true both in solar cycle 21 and also in 20. So we'll be looking at that later. This is the maps that we start with that Ian and Hewins and Bob McFadden have been working on for years, initially with Pat Mcintosh himself. He started in solar cycle 20, 1968, I think. And then we added another solar cycle 19 from Kodaikanal. So we have 55 years of these neutral lines, or polarity inversion lines, or you also can call them polar crown filaments. And we have 35 years of coronal holes, of which Ian just finished a solar physics article that was accepted. So congratulations, and check it out. This particular map here, Carrington rotation 1751, is for solar minimum in July and August of 1984. What we do is we find the coronal hole starting from the pole, and we go down until we find the coronal hole boundary. And for this case, we only look up to 50 degrees. So when there's an extension, a low latitude extension, we don't call that. And this black line is then the median of that coronal hole boundary. And similarly on the south. We also will then, from the coronal, starting from the pole, go down and find the first polarity inversion line, the first neutral line. And that one we call the primary pill. And in this case, it's at 50 north and about 40 south. And we picked, you see these dashed lines. There's a dashed line at 37 degrees, back up, at 37 degrees because of this particular Carrington rotation. We're trying to get enough primary pill so that we have enough data. So we have a primary pill here, a little bit there, and here. And often what we'll see is we'll find a primary pill, and then right below a primary pill, we'll find the secondary pill. If we don't have a primary pill, we don't look for a secondary pill. So the primary pill is found down to 37 degrees, in which case we quit looking. And then we find from the primary pill a secondary one, and we look down to 22 degrees, which is 15 degrees less. And we do that because that is the distance that Pat Mcintosh found in 2003 between those two. So that's what we have. And they're usually segments, but we find their medians. And we have 732 of these. So it's a very nice database. So this is the next example. This is early in the rush to the pole in solar cycle 21. The coronal hole is just a very small amount. I can't even point to it. Let's see where it is. Back up. Okay, so here's the coronal hole. It only encompasses 10, 20, 30, 40, 50 degrees of longitude. And what you see is this polarity inversion line. This neutral line is extremely close to the boundary of the coronal hole. It's only 3 degrees difference. And that's also true in the south. It's very close to this coronal hole extension. But the coronal hole boundary itself is not including this extension. It's the first boundary you find, which happens to be down at 70. So we have our coronal holes here, a very small amount. We have the primaries, and we also have the secondaries. And here what we see is this chevron shape, which is determined from differential rotation, because things are rotating faster. I think it's faster at the equator and slower at the poles. This is the next example. I took it from the end of the rush to the pole from solar cycle 19. One of the things we find is we find almost continuous secondary polarity inversion lines or polar crown filaments. And so that's certainly the case here. If you just looked at this by eye, you'd say this is our primary and this one is our secondary. But because it's an automatic routine, this is my primary, and then from that longitude on, my primary is over here. So the primary is being shared with the secondary on this same polar crown filament. And we then have extra segments of the secondary over here. But again, like I told you, the medians really tell a very nice story when we do this. For this particular stuff, we're taking it from the Kodaikanal images, H-alpha images. It's an atlas by Makarov and Sivaraman in 1986. There are no active regions, there's no sunspots, there's no plage regions, and there's no coronal hole data until we get into particularly this helium, 10, 8, 30 angstrom in solar cycle 20. Some of the things we find in solar cycle 19 are hyperlong filaments. The filaments are these green segments, and they're a little hyperlong for this. And often we don't see any at the very highest filaments or highest pills, even though when we check back using Madone data, Bob McFadden and Ian found them. This is the next thing we look at. Since a lot of the previous studies have used filament locations. We want to compare the filament locations with the pill locations. So for us, the maximum filament location is either at the maximum pill location or it is more equatorwards, just by definition. And for the solar cycles that Pat Mcintosh did from solar cycle 20 to 23, the median difference is actually 0, which means they were the same place. But if you take the average, it's a degree 0.2 for those. And for solar cycle 19, it's 4 degrees. If we look only at in this rush to the pole, where you have at least 2 degrees different between the filament and the pill, then the average is 6 degrees for these cycles and 12 for 19. So that shows you there's some problems in finding filaments for solar cycle 19, but in general, we think that when we look at the maximum pill locations, we're going to be okay. These slopes, these solid lines, are actually from the maximum pill locations. And you can see for solar cycle 20 through 23, they line up really well with the maximum filament locations. And they're a little bit off then for solar cycle 19, but we think that when we compare with studies that used filaments and we're using the maximum pills, we actually get similar answers. And ours actually should be better because we have more longitudes with them. So this is the comparison we did with Pat Mcintosh. He did a study in 2003. And what he did is he flopped again the southern hemisphere onto the northern hemisphere. So this is solar cycle 20 and 21 and 22. The reds and pinks are the southern hemisphere, and the blues and the greens are the northern hemisphere. So you see this rush to the pole, as was on the opening slide, the primaries and the secondaries. And what he found is there was this about 15-degree difference between them. For solar cycle 20, it looks kind of a mess because there is one rush, and that's the southern hemisphere, a second rush in the northern pole, and a third rush, which is this kind of dotted line. We actually tend to see 4 in here because right at this location, he skipped some Carrington rotations, 3 of them. And if you look down here at our maximum filaments, they go to much lower latitudes. And that's because the polarity changed. The value of the pole changed for those 3 solar cycles. So he just ignored it and called it 3 rush to the poles. We actually think there are more like 4, but that's fine. It looks good. The other thing we have different is it looks like there's this increasing difference between the slopes of the primary and the secondary. So it starts about 10 degrees apart and ends about 25 perhaps. This is another one, the same period, but what we're doing here is we are looking at the maximum locations for the polar crown filaments, and here we're looking at the median locations. So the difference between the two is about 7.5 degrees, but it's a much cleaner story. So this is similar to what the filaments would show, but when you clean it up with medians, look how much cleaner it is. You see oscillations. This is what we're looking at. You see these 20 Carrington rotation, roughly, oscillations. So we're going to be looking at that in more detail, but one of the things we do want to look at is these diamonds are at the peak polar latitude of the secondary pills, which become primary after the rush to the pole. And so in the southern hemisphere, it's peaking just about 60 degrees, and in the southern, it's also about 60 degrees before it heads off into these oscillations. This is the full 5 solar cycles. So this is the northern hemisphere, the southern hemisphere. This black line is the difference between the primary and the secondary, which tends to be, here's a dotted line at 22 degrees, so it tends to be about maybe 15 degrees perhaps. And it's least in the period between solar max and solar min, which I'm going to be calling non-rush, as opposed to the rush to the pole period, which is between solar min and solar max when things change. So there's a couple of things to look at. Here we see multiple rushes to the pole in solar cycle 19. There's 3. Here's the 1, 2, 3, 4, with a period where it just stalled out in solar cycle 20. In the southern hemisphere, we have a couple of rushes in 22 and 23. And some of the things that we see here is there's drops, 10-degree drops in latitude of these medians, particularly in this secondary pill. So here's one where it drops abruptly. And so I just called that the beginning of another rush to the pole. It drops here abruptly, 10 degrees in both the primary and the secondary. So this is now the start of the rush to the pole for that one in the northern hemisphere. The other drops that are 10 degrees are in solar cycle 21, 23. So the other thing that was kind of bizarre is there's this increase toward the poles over about 8 Carrington rotations in the southern hemisphere right before it's rushed to the pole. And I have no idea why that is there. And I won't look at it anymore. So now we're going to go look at the next one. I wanted to look particularly at the coronal holes. And let's back up one. The coronal holes start in about 74, and they are these pluses. So they are roughly 16 degrees poleward of the primary pill. They have their own rush to the poles. They have also similarities in some of the oscillations with the pills. So we're going to look at the coronal holes a little more. So this is a plot showing those coronal holes, the same ones. The only thing different about it is I have put in magenta the first one after solar max, and in green the first appearance of that coronal hole, and as we saw in the first example, was only about 60 degrees in longitude. And then I put in green, which you can't see too well, when you have a persistent coronal hole, polar coronal hole. So it's most longitudes around the sun. The other thing I put in here was the stars are the maximum latitude of the end of the primary pill rush to the pole, and the diamonds are the latitude of the secondary rush to the pole. The dotted lines, the dashed lines here, are solar min, and the blue are the SILSO solar max, and the red is the different SILSO solar max for the southern hemisphere. And the solid line, red and blue, is the changeover in polarity from over 60 degrees using, in this case where it looks kind of ratty, is Mount Wilson Observatory, and in the smoother case is Wilcox Solar Observatory, right? So the red is the southern hemisphere and the blue is the northern. And I've added here a proxy from the facular counts from Munoz Jaramillo. And they're a little bit smaller in magnitude. They're about 3 times smaller in magnitude. But they do show at least where things cross and change in polarity. So this particular table shows things like, when do you have this polarity reversal above 60 degrees? When was your last primary rush to the pole in Carrington rotations? And this lag is in Carrington rotations after this switchover. When is your first polar coronal hole, where the first 2 in solar cycle 20 are from Mauna Loa's MK2 experiment that Dave Webb found. When is the first persistent polar coronal hole, where you have pretty much all longitudes, where this is the lag between the first and the second. And you can see on average, it's about half a year later. And what's interesting is it comes up a lot sooner in the southern hemisphere. So it's only 3 to 5 Carrington rotations in the southern hemisphere after the first appearance, compared to 7 to 8 in the northern hemisphere. And this is the lag from that polarity reversal above 60. And then finally, what is the end rush to the pole for this secondary pill? And so sometimes it turns out that the northern hemisphere, the secondary pill peak, is before the persistent coronal hole, but it is after in the southern hemisphere. So sometimes there's a considerable difference. There's also a difference between this one and its polarity reversal, almost double, in fact. So the South Pole takes longer to arrive than the northern hemisphere. So we have some questions here and some comments. The first polar coronal hole often occurs right after the last primary pill rushes off to the pole. And you can see that here. So this is one different, this is one different, this is one different, this is the same time, and this is one different. So it's really quite common. As soon as the pill clears itself away in the polar region, then the coronal hole comes up, and it's a different polarity, of course. So the first polar coronal hole is about a year after the polarity reversal. So that's in here. And the persistent coronal holes are about, you can't see it, but it is about half a year later. And there are differences in the southern and the northern hemispheres. So now we go on. This is the maximum pill locations. They're 9 degrees poleward of the medians, roughly. We do have the primary slopes, and what we do see is we do see this slower slope for the secondaries than the primaries. It's not quite as clean, but we do look at this because we want to compare with other studies. So that's what we'll do. Often the difference is a little bit larger, though, than the 14 degrees. So this is our first comparison. This is with Yan Xu et al. He did a 2018 paper in AppJ Letters on the filaments from Big Bear Solar Observatory and Kanzaholi Solar Observatory, looking at filaments above 40 degrees from the H-alpha images, and he finds this rush to the pole slope in red for solar cycle 21 through 24. So we compared the 21 through 22. He also put down here the magnetic field. Here it was the radial field, pretty much close to the, that's in Gauss on this side, pretty much close to the full field that I will show later. These are Kit peak line of sight values, so they're going to be smaller in magnitude than these guys. But we're going to look at these slopes first. And you can see that most of the time they start about the same time, but they usually don't end close to the same time. So this is our comparison tabular form. And the ones in red are where we're off with the error bar. So, so we're off not quite half the time. It's a reasonably good comparison. These values tend to be a little bit lower than what we have, but not always. So, but we're pretty happy with it. So the next one, this one is from Dick Altrock. He looked at the green 145303 angstrom coronal line with a yearly smoothing, and he added the northern hemisphere and the southern hemisphere together. So we're looking at here solar cycle 21, 22, and 23, where I put our slopes in based on his 2003 paper that gave the slopes. So we compare the shoe with our median and max and his combined. And what we did here is to look at the variations. And there's sometimes quite big variations in these slopes because the northern hemisphere and southern hemisphere are quite different. So this is the only one that's a little off, and it's only very little off because 63 and 21 is equal to 84, which is the northern hemisphere value, whereas the southern hemisphere value was 42, so it was quite a big difference. But I would call this quite good. I'm pretty pleased with this one too. Even though the iron line is a little bit different. We think it's streamers for this upper latitude region. We think this is more active regions. So I'm pretty pleased. We did another final comparison. This is with Hyder. What he did is he took Meudon H alpha data and put in all of his filaments that he saw between 40 and 80 degrees. And we see actually 1, 2, 3 rush to the poles, which we saw also. And then this is the non-rush period from solar max to solar min. Now in the southern hemisphere, he had less coverage. So we actually ended our rush to the pole at this star, whereas I quit the slope right here. But even so, we did pretty well in this, comparing the number 1, number 2, number 3, and then the southern hemisphere. So pretty nice. This is a comparison I just put in today. Yan Shu told me last night that his paper was accepted. This was also at the Fall AGU where I found it. It's 100 years of polar crown filament migration, and it's been accepted now, congratulations, at the Astrophysical Journal. So it will be a 2021 reference, and he uses the Kodaikanal H alpha images most of the time, and a little bit from Big Bear and Kanzaholi to find the rush to the poles. And all of the slopes are larger than for the previous study and in better agreement with the present study. So the red is where we're not agreeing too well, and sometimes it's because he's looking at a different Carrington rotation into the rush to the pole than we are, so our values are already pretty far, pretty low. So we have a low slope and he has a high slope. So, but in general, I would call all of these pretty good agreement. So that's good to know. So let's go back. This is just another plot of the medians that we're looking at. And one of the things we have to do is we have to do a little bit of adjusting, and then we're going to smooth it over 3 Carrington rotations. And we do this to get out more noise. But some of the things we have to do are, for example, if we look here, here's the end of the rush to the pole. And the next one, you can't really see it, is right there. It's on its way down to the primary pill. So it's obviously in a halfway state. So we adjust it so that we take it, so it's an average of the 2 following. And we change then the secondary location as well. Some are just plain out of line, like this one, and for the northern hemisphere and southern hemisphere in solar cycle 19, so we delete them. And other things we do is, you maybe can see this little diamond that is above, so it says the secondary is polewards of the primary. Well, what that means is you just have a very few number of secondaries, and it happens to be above. So we adjusted those. There was only 3 of them in the beginning of solar cycle 19. We adjusted them downwards 8 degrees, even though the average here is more like 12 degrees different. But so those kind of adjustments we made, and we also deleted the coronal holes that were very low longitude numbers in the solar max area where they disappeared. And a final thing that we did is we have some coronal holes that we found from EUV on the manned Skylab experiment, and they tend to have kind of larger polar crown areas than polar cap areas than the other data. So we deleted all these EUV observations and only stayed with the 10,830 angstrom. We have a few MK2 estimates also. So the next one. So this is after we've done the 3 Carrington rotation smoothing. And you can see how smooth it looks. It looks really nice. We have a lovely data set here. So down here is the distances. So this is 54 Carrington rotations in this rush to the pole, 83 in this non-rush area. So the longest non-rush area is 117 Carrington rotations, and it's going to be even longer because we didn't quite get to the next rush to the pole. But some are really long anyway. This southern hemisphere is 107 Carrington rotations. So some of the things we see is we see this solar max secondary rush to the pole ends at 67 south. This is the highest it goes in all of these 5 solar cycles. We see oscillations in the coronal hole boundary, which seem to mimic the primary coronal hole oscillations. And we see this is very unusual. This is an early end to the rush to the pole in the secondary pill. So it actually peaks before the primary does. It's the only time in the 5 solar cycles that it does. And finally, we see this drop that goes, it starts first in the coronal hole, drops 5 degrees, which increases the coronal hole area by 50%. And then the next CR, it's in the 2 pills by 10 degrees. It drops back up. And then it is about 8 pills, and then it's over. It's first in the secondary pill, and then it's last in the primary pill and the coronal hole boundary. So it's obviously something that's going from the south to the north. And so we'll be looking at that at the very end, but it's a 15 degree per Carrington rotation movement. Some disturbance, probably in the deep. So what we did first is we wanted to look at the transition pills. Maybe I should back up. So what we're looking at here is, for example, I'm looking at the primaries. Back up. Primaries in the non-rush period, and then the secondaries in the rush. Primaries non-rush, secondaries rush, primaries, secondaries, primaries, secondaries. There's this transition to this peak, the end of the rush to the pole of the secondary. And so this is what we are particularly looking at, this transition from the secondary to the primary in solar max. So this is here. And we find, again, the rush to the poles, but here we're looking at from the secondary through the primary. And it's a smooth continuation. So we will look at that, and sometimes we'll find various slopes. If the slope is too long, then we do a shorter slope. And so it's 25 Carrington rotations here, it's 12 Carrington rotations there. We have diamonds at our transition peaks, and we try and do a fit. One of the things we have to do is, if we're going to do a harmonic analysis, we can't just do it on the locations. We really need to remove the mean and the slopes. Like, you can't really put in this slope for the rush to the pole. It's not going to give you anything in your oscillations that you want to see. So what we did is we first did a superposed epoch analysis, and we took the 0 as this transition peak. And so the only one, these diamonds are in the rush to the pole period of the secondaries, and the solid lines are the primaries afterwards. And the only time where we have diamonds at the peak is that one time where we had an early peak to the secondary polarity inversion. And this one is where we take the medians of all 5 in the northern hemisphere and the medians of all 5 in the southern hemisphere. And one of the things you see is that the peak occurs later in the southern hemisphere after the rush to the pole for the primaries ends, and it occurs much sooner for the northern. But the width of this peak for both is still about 16 Carrington rotations. Now, here, the oscillations almost look like they're gone, certainly in the northern hemisphere where they are smaller to begin with. But we do see this 20 Carrington rotation peak for, I believe this one is solar cycle 21. For solar cycle 19, it's more like 18 Carrington rotations. And for solar cycle 23, it's more like 35 to 40 Carrington rotations. And that's where it has the abrupt 10-degree shift. So we're looking at these. We have looked at solar cycle, the 5 solar cycles here, and that's where you get the averages. So the northern hemisphere is 3 Carrington rotations after the end of the primary, and the southern is 9. So we're looking now at the wavelets, and the first thing we do is we find this zero baseline where we remove the slopes. So this is the zero baseline plotted for the coronal hole boundaries. The red is for the primary pills, the magenta is for the secondaries, and the purple is for this transition one where you go from the secondary RTTP to the primary pill in the non-rush period. So what we're doing is first, here's the coronal hole boundaries, and it's wavelet analysis, where the period goes from 10 to about 50 Carrington rotations. We have an absence in the solar max period where we don't have any. All of these are, so it's the same value. So the red is the same in all of these plots. I do list the highest amplitude, which is, I guess it's 5.2 degrees in the primary. And that is located in this right here at 14 Carrington rotation period. So one of the things we see for this southern hemisphere is we see red values mostly at this transition area where the secondary RTP peaks in the solar cycle 19, solar cycle 21, and solar cycle 23. In this period from 23 non-rush period, we see a high and then a low, so it's about 35 to 25 in all of them. And we did an FFT transform for everything also, and we find the same thing. So we find in the first part approximately 35 Carrington rotations between 44 and 22. And in the second part, it's closer to 20 to 25. And back up. So we do find periods, though, between 10 and 35 Carrington rotations. So we're going to look at this later. This is the FFTs for the southern hemisphere on the left and the northern hemisphere on the right. For the rush to the poles on the top and the non-rush periods on the bottom. These was what I showed in the previous plot. One of the things that happens here is FFTs are dependent upon the number of Carrington rotations in the sample, which happens to be 44 here. So you get this 44 peak, 22, and then a third of that is like 15, etc. This is the wavelet. It's kind of nicer, in my opinion. This is for the northern hemisphere. The zero baseline pills and the coronal hole boundaries, primary, secondary, and the transition peaks. And we do see these consistent large amplitudes right at the change over in solar max to come on all of these. So this is where, oops, back up. Let's back up again. Okay, so this one is for the primary inversion, polarity inversion lines. And the lines are from the wavelets, and the histogram is from the FFTs, where I've multiplied the FFTs by 60 because I only did 11 periods which are 5 rush to the pole and 6 non-rush periods because of that break in solar cycle 23. And if I divide 732 maps total that I did with wavelets by 60, you get about 11. So that's why. So it's now about the same amplitudes. This is the rush to the pole periods, which is about a third of the time. We see a peak around 25 Carrington rotations for this southern hemisphere. We see it also in the non-rush, around 25 Carrington rotations. We see it in the total. It's not as present in the northern hemisphere, which is blue. So the other thing I did is I did the average pill, which is the primary and secondary. And that's in green. And it has a little lower amplitude, particularly lower in 16 Carrington rotations, which is that transition peak from the secondary rush to the pole peak. And since we're fitting it in this transition, it's going to come up more. But we also see a 20 Carrington rotation peak, particularly in the non-rush period, and we see lower, smaller, shorter periods that are between about 7 and 10 Carrington rotations. Back up. Okay, so this is for the coronal hole boundaries, and we want to see if we have the same characteristics. It turns out we don't have a major 16 Carrington rotation period because there's only one coronal hole boundary. But we do have this 20 Carrington rotation is its major peak. The southern hemisphere tends to be larger than the northern. We see this 25 Carrington rotation period in the non-rush and the total, but it's also in the sometimes in the rush to the peak. These tend to be more, the shorter wavelengths tend to be more for the northern hemisphere, and particularly in the rush to the pole, but not always. So we do have similar peaks. It's good to know. And back up. And back up. Okay, so this one I wanted to focus on this 15 degree per Carrington rotation disturbance from the south to the north in 2005. So it expanded the polar coronal holes 50%, first in the south and then last in the north. That's a pretty big expansion. This is the race as it goes from south to north. And I got here from Sharon Howe 2016, her meridional flows and 5 Gauss unsigned magnetic flux. So in the equator, this is where we have this rush to the pole from the south to the north. We can see that there's an increase in the meridional flow at the equator. There's also an increase in this 5G magnetic flux. So things happened when this occurred, and we'd like to know a little more what happened. Back up. Okay, so this is my conclusions. We have a rush to the end of the secondary pill. It's in the transition when it goes from the secondary to the primary. And so this peak, which is about 57 degrees latitude, leads to this 16 Carrington rotation oscillation. We do have other periods which we share with the coronal hole boundaries. We have a 25 Carrington rotation, mostly southern hemisphere. We have a 20 Carrington rotation and the shorter Carrington rotations. We also see a distinct 15 degree per Carrington disturbance from the south to the north in 2005. And we would really like to know what happened here. And we would also like to know what happened in the interior to explain the lags from the polarity changes in the coronal holes, the first appearance of the coronal hole, and the things that seem to be different also in the south and the north hemisphere around solar max. So that is about it. I had one final one on looking at differences in solar B field from various sources. And one of the things I found particularly interesting was this can go back to like 1905 using facular counts. This is from Munoz Jaramillo. So this is solar cycle 23 when we have a low B field, and then it was higher, and it's actually much higher in the past, but we don't have satellite data then. So I'll go back to my previous slide, and I guess I am done. So I will take any questions then. Nick, and shall I stop sharing the slides or not?
You can leave them if you want, in case anyone has questions that you want to point to something on the slides.
Okay.
So does anyone have any questions? You can type them into the chat, and I can read them. Maybe while we're waiting, I will ask one question. You show this difference between the northern and southern hemisphere. Sorry if this is sort of naive question, but do you know the source of why they're different?
No, I'm asking modelers.
Okay.
But one of the things I would like to point out is one of our participants is Dick Altrock, and I'm grateful for his work in looking at the iron line and rush to the poles. So thanks for joining us, Dick.
So there is a question here, and it says it may not be related to the topic, but what is a switchback pills? And if you could explain.
Switchback pills or transition pills? Must be transition. Okay, transition pills. How come I'm not getting this? Oops, that's not the right one. This one. Okay, that's probably easier to explain. Okay, the transition pills are when I go from a non-rush primary pill to a secondary pill in the rush period. Or it's actually the other way, it's in time. So you go up the rush to the pole with the secondary pill, and then you come down. It's the same polar crown filament. It's not different at all. It just changes because the primary one has gone off the top of the globe and changes polarity. So this is a single polar crown filament line. If it was continuous, but we saw, of course, they aren't. So these are the transition pills, or the secondary to primary. And they are every solar cycle. But because we have, and they are shown here where we look at them continuously. So that's what we're looking at. We're trying to look at this peak in the secondary pill rush to the pole end, and to find out what characteristics it has. And it turns out it also ends up having oscillations afterwards a lot of times, not always, but a lot. So that's about all I can say there.
And Sarah did make a comment. I don't know, Sarah, if you want to just explain.
I guess maybe just to clarify if that is what Shaktida is asking.
I mean, I was reading this paper on global solar magnetic field evolution using Mcintosh archive by David Webb, and there I came across this term of like the switchback PILs, so which I was a bit confused, so I just thought of asking.
I suspect that if it was in Dave's paper, he was talking about a switchback, which is a different. Barbara's plotting the latitude versus time, right, and showing how it changes from one Carrington rotation to another, and then much longer time scales. But if you look at the large scale structure you can have a you can have one of these polar crown type things, which has a real bend just in a snapshot in time. If you were just looking at the disk of the sun, you would see a sharp bend in the neutral line versus latitude and longitude. And that kind of sharp bend, that point is often associated with where coronal mass ejections erupt. So I suspect if it was in Dave's paper that he might have been referring to that, which is a different phenomena.
Okay.
Yeah, switchback I hadn't heard of myself.
Yeah, fine. Thanks.
All right. Are there any more questions or comments?
Yeah, maybe I'll just add up, like, I don't know whether it's the right time. I'll just take this platform, like, I'm Shaktivel Pillai, and I'm working with Mikhail Shwanda here in Prague, in Charles University. And also I'll be working with Ian and Michael Kirk. So the last slide, which you are mentioning about, like calculating the solar B field, maybe I'll be contributing a bit through my work also, but that would be soon. So something I would be interested in talking with that also later a bit. So maybe
Okay.
I noticed Dave Webb just hopped on. I wonder if he wants to answer the question about the switchbacks. Put him on.
No, not really. Thank you.
Did you mention switchbacks in your paper, and did you mean the ones in the large scale corona where CMEs are sometimes associated with the bends in the neutral line?
Yes, that was a common theme involving Pat, as a matter of fact, back in the 80s and so forth. We saw the switchbacks and film eruptions were involved, and the complexity seemed to sometimes lead to CMEs. So that's why they're of interest.
If there is anything, I'll just write either to Ian, and then he can forward it to either Sarah or like David. Thanks a lot, guys. It was a good talk.
Yes, it seems there's no more questions. Thank you, Barbara, for a nice presentation.